Now, those mnemonics sometimes come in handy. All right, now the last thing is that because the neutron has no net charge, we can change neutron number. Okay? Neutron has no charge, so this means you can vary the neutron number without changing chemical identity, because chemical identity is fixed by the proton. And since we don't have to charge compensate, we can add or subtract neutrons at liberty. And so you can look, for example, at the periodic table. And if you look up the atomic mass of carbon, you'll see that carbon comes at 12.011 for carbon. 12.011. Well, isn't this against Dalton? This thing's supposed to be a whole number here. But if you look more carefully, you'll find that this is a blend of 3 different forms of carbon. We have carbon 12. I'll even leave off the 6 because we already know it's carbon. It has to have 6 protons. So carbon 12, we know that it's got the proton number by definition is 6, and the neutron number, 6 from 12, is 6. So it's got 6 protons and 6 neutrons, and it is the dominant form of carbon. So its abundance in nature is 98.892%. 98.892%. There is a carbon 13, however. So it axiomatically must be 6 protons, and it's got 7 neutrons. And this is found in the abundance of about 1.108%. And then there's the last form, carbon 14, which is the radioactive form, and we'll talk about that later in 3091 and its use in radiocarbon dating. And carbon 14, 6 again, and it has 8. And it is found in vanishingly small amounts, 10 to the minus 12, or part per trillion. Part per trillion. So if you add all these up, then you end up with 12.011 as the atomic mass. So we have here, they all have the same Z, same proton number, okay, but different A. Different A, which means number of neutrons varies, okay? So that means they're found on the same place on the periodic table. So if they're found in the same place, it's isotopos. So these are called isotopes. Isotopes have the same chemical identity but different nuclear properties. What are the units here? We write 12.011. We're writing 12.011. It's either grams per mole, and I'm not making a mistake here. Most of chemistry has gone SI. So every mass should be in kilograms, but occasionally there's this one little remnant of the old CGS systems, centimeters, grams, second, and this is one. So this is 12.011 grams per mole, or 12.011 atomic mass units. Atomic mass units, AMU. And the AMU is defined as the mass of 1/12 of a carbon 12 atom. The mass of 1/12 of. So I talked about this concept of mole here. What is the mole? Mole is a more practical value, something that we can handle tangibly. And how do we get the value of the mole? The mole is something that was also defined in terms of carbon, and the mole is defined as the mass of, it's the amount of carbon 12 weighing exactly 12.000 grams. So you can see the atomic mass unit will then give you that the atomic mass unit will be 1. Let me go at it a different way. This will be the definition of the mole as the amount of carbon weighing exactly 12 grams. So I'd like to know now how many particles, how many carbons are there in that mole? And one way we can get to that is by looking at two pieces of data. The first one, again, is by Faraday. Faraday, who conducted electrolysis of silver. Electrolysis of silver. In an aqueous solution, he passes electric current and he causes silver ions to deposit and form metallic silver. And he measures how much charge is required. He has current, right? We know that charge is equal to the integral of current times the time. And he knows the current, he knows how much time, and then he weighs this. So he's able to weigh the silver and compare it to carbon, and against that scale, he finds the silver weighs 107 grams versus 12 grams for carbon. So that's the ratios. Now, if he only knew what the electron brought him, he'd be able to divide through and calculate how many species there are in a mole. And in order to determine that, we had to wait a few years till 1909. In 1909, Robert Millikan, doing experiments at the University of Chicago, conducted this interesting effort where he took atomizer, filled it with oil, and then squirted fine droplets of oil mist in between two plates that could be electrically charged. He further charged the droplets by irradiating. Here it's showing X. He used X-rays. He used various forms of high-energy radiation in order to make the droplets bear a charge. So now you have this situation where you have a droplet that is net negative or perhaps net positive, and it lies suspended between two plates, and I'm able to vary the voltage on the plates, making this, for argument's sake, negative, and this, for argument's sake, positive. So if there's no charge on the plates, these droplets will simply fall under gravity. Once the droplets are charged, it makes no difference whether there's... they will fall regardless of the charge. When the charge is applied, if the upper plate is negative, we would expect that the negative droplet would be repelled at a rate exceeding gravitational fall. The positive droplet, its fall will be slowed and could even be made to lift. And so by playing with a variety of sizes, remember the atomizer is going to give a distribution of droplet sizes, a distribution of voltages, Millikan was able to develop a relationship between the applied charge and the observed velocities of the droplets. So let's plot droplet velocity as a function of looking at the number that have this velocity, with the 0 being in the center here.